now let us understand the capacity fade due to DOD limits. Now this is a graph which we have assumed for NMC cell which is of 3.25 Ah, and let us see how the capacity falls due to DOD limits. Now this is the actual window which is having from 2.5 volts to 4.2 volts. This is the maximum voltage and this is the minimum voltage. For that, when we have a standard condition which is 0.5 C discharge, we can see that it has a rated capacity of 3.25 Ah. Now when we chop off the charge stresses area and we make it the maximum voltage 4 volts and we limit the minimum voltage to 2.8 volts, we could see the portion where we have removed, there is a capacity drop, and that comes to usable of 3.0 Ah, which means when we chop off the voltages, we can see that there is a voltage drop, but by doing that we limit or we eliminate the charge and discharge stresses, which helps in improving the life cycles of the cell. So what are the advantages? Now let us, as we saw the presentation, now we'll understand what are the advantages of the DOD limit. Now when we see what are the advantages, we can see that there is a capacity fade. Could not be an advantage, it's a limitation, but the usable capacity is less than that of rated capacity. But the cells will never witness any of those voltage threshold limits. So by doing that, we are avoiding high temperature generations, avoiding high internal resistance, and by doing this the life of the cell is increased, which means the internal heat generation is parallelly reduced. And also at the end of the maximum and the voltage band where we have double or triple times of internal resistance rise up when we saw in the previous week, that is eliminated mainly. And one of the most important thing is SEI layer formation. So when the cells are not stressed so much, the SEI layer formation happens slowly. It is gradually, the speed of it is reduced, and by doing that we won't allow the cell to witness its thresholds, and the SEI layer is usually responsible for the dendrite growth or lithium plating on the anode, which causes internal short circuit. And the reason for that formation is something which we have attacked, and we have reduced that to a greater extent that the SEI layer would form, but it would not form at the rate at which it has formed by controlling the DOD limits. So that is the advantage we get majorly, which means the life cycle of the whole cell can be increased. Now we'll understand what are the BMS C rates and protection features. So we have till now understood what are the parameters like voltage cutoffs, cell balancing, and also a few terminologies, and which are the basic functions of BMS. Now we would also go through the BMS protection features. Here BMS charge protection feature. So here we can see a cell is being charged based on a common charge protocol, which is CC and CV, which means CC is called constant current and CV is called a constant voltage mode. Initially the battery pack is charged at a constant current always and up to a certain amount of voltage build, and then the charges enters into a constant voltage mode, and which means the voltage is constant and for a small duration of time, and then the volt, that is basically for stabilizing the voltage, and also the cell reaches the maximum capacity required. So here is the graph which we can see there is a voltage and there is a capacity, and this is the current. So basically if we see when there is a constant current being passed, you can see voltage builds up slowly. It slowly gradually builds up, it has reached its point, and then after a certain time it will not increase anymore and it's into CV mode. It has become a constant voltage and the current also slowly drops hereafter. But if you see the capacity curve, it still needs some more time. After the CC mode, it still needs some more time to build its 100% capacity, and that is where which happens in the constant charging mode, constant voltage mode. So there are two modes, constant charging and constant discharging, but still that happens. But if you see at the current, it still drops, but there is still certain amount of current which is still be going to the cell. When that is there, the BMS which usually does is it stops charging after the minimum current it has reached. For example, if it is charging at 0.5 C over here, if you see it is charging at 0.5 C, which is 1625 milliamperes, it will charge up to a constant current mode, and at a constant voltage mode you can see it is gradually reducing. So which means we have to program the BMS saying that if it is reaching a 0.2 amperes or 0.1 ampere, the charge will completely cut off. So the BMS will not allow any more charge to go to the cell, because it has reached its threshold of 4.2 volts, and it has also reached its capacity which is meant to be. So that is how you program the BMS as 2.5 volts, 4.2 volts as a maximum voltage with a cell capacity of 3.25 and C rate. If anything is going more than that, the BMS would definitely disconnect it and maintain that once it is reached its 4.2 volts and the required current rate is met, the BMS terminates it. So what happens if this is not working? So you might have observed in your daily life scenario when most of the people have a habit of putting your cells for charge and you leave it overnight. Initially, for the first 1 month or 2 months or 3 months or 4 months, if it's a brand new cell, you would not even observe that. But what happens is your cell is, even though if it is cut off, your cell will still be receiving that amount of charge slowly. And when that is done over a period of time, your cell is deteriorating because it is constantly at a high voltage. When a cell is at a constantly high voltage, as we saw in the previous graph, when it's always at 100% SOC, your internal resistance is always high. And there is no way that your cell is being discharged because the charge is being pumped in, and when that happens, your life is going to be affected. So after a period of time, your cell, your mobile phone which you would be using for a whole day without any charge would slowly reduce to maybe instead of 24 hours a day, it would reduce to 23 hours, and then slowly it will come down to 24 hours. And then one common tendency what we all feel is, now it's been few days, it's been few months, now the cell has started deteriorating, let us change to a new cell. But that's not the case. It's because of the human pattern that is happening. We are forcefully allowing the cell to deteriorate by allowing it to charge for a longer period of time. So that is what happens with BMS. So the same happens with the BMS charge protection. Even if BMS has to disconnect it completely, even if it is disconnected, we should be careful enough that it is not anymore connected to the charger, because there will be certain amount of charge which will always be flowing through it, and the cell or the battery pack will always be at high voltage potential where the internal resistance is always high, and a cell or a pack having such high internal resistance is not good at all. So that is the BMS charge protection feature, where the BMS actually disconnects it after it reaches its maximum set voltage range. Then we have the same for discharge protection. So when we have discharge feature, the maximum voltage is 4.2, and we have a minimum voltage of 2.5, which is chemistry dependent. Once the voltage is reaching its 2.5 volt, it will disconnect at that point of time. So here I would like to emphasize something more, which is actually to make you understand what is the capacity and its C rate availability over here. Firstly, let us understand the BMS protection feature, which is like, now the cell has been discharged completely and it has reached this 2.5 volts, and after that the BMS would cut off, and anything, if the cell is, the motor or the controller is asking for more power, the BMS would straightly communicate that there is no more power, and the BMS terminates the whole command itself there. But if we want to have higher discharge capabilities, if we want to discharge for a longer time, as we know, 0.5 C is for 2 hours, 1 C is for 1 hour. But it would also have an impact on the capacity delivered. Now, if we see, there are three graphs, 0.2 C, 0.5 C and 1 C. 0.2 C is something, when you discharge at 0.2 C, you can see that 0.2 C is actually more than what the typical capacity of the cell is. The cell is actually of 3.25, and this 0.25 C, if it is extended, it can go up to 3.3 or 3.4 Ah. Whereas if you see 1 C, it is limited to 3.25 only. So, which means if you
discharge the current at smaller or standard rate, the kind of power which you can discharge or deliver would be slightly higher than what your actual normal condition is.
So, which means you will also have to choose the right C rate as per the load profiles. When a battery pack has to be designed, when a battery pack is designed for an application, you should also see that what is its C rate, and when you choose a cell, you should also understand what the cell can deliver at that C rate and how is its capacity being affected. Here it's matter of 0.5 or 0.25 Ah, that is fine. But there are some certain cells which can have a major impact when you operate at 0.25C and 1C and 3C, which we saw in terms of internal resistance. That is the same which would happen for this as well. So it is very important to see that where do we limit our C rate, how much of it has a capacity difference when it is discharged at a lower C rate, and how is that capacity difference being affected when it is discharged at higher. So nevertheless, the BMS is being programmed with that protection feature of saying if it is reaching 2.5 volts, anyhow it's going to be disconnected, and also it's also going to have that protection feature that it is going to be discharged at higher C rate even though it is going to disconnect it. Then we have one of the most important feature, which is BMS temperature protection feature. So as we know, whenever the cells are operated above the operating temperature, there could be an impact. Like the main reason is like the electrolyte which is there in the cell could dry up, and that would leave no medium for the ions to transfer. So the BMS helps in monitoring those hotspots. Like we discussed, like we know that there are NTC sensors placed throughout the battery pack, and those hotspots are actually arrived by doing a thermal simulation and understanding where do we have a hot, and by placing the NTC sensors in that place, the BMS can take an appropriate action to stop or limit the C rate. Like for example, if the battery pack has reached its maximum temperature, that is not throughout the battery pack, it could be only at a hot spot where the sensor is. That means the other portions of the battery pack are still cold. By doing that, BMS has two ways: either it can terminate the whole battery pack, or what it could do is, instead of discharging at 1C or 2C, it can slightly reduce that discharge rate. It can slightly discharge at lower C rates, maybe 0.5C or 0.2C. By doing that, it can still allow the pack to function, but at a lower C rate. So that is one advantage. That's how you can program the BMS to be more effective and more powerful. So this is one feature that you can always test it. Like for example, if you have your mobile phone, you could keep it under the hot sun, and you can feel that your mobile is warm. Then especially if you're using the latest 5G phones or latest phones, you can always have a display on your mobile saying that your mobile is hot and you have only limited access. So that is actually a protection done by the BMS considering the temperature that the cell has been experiencing. So that is one protection feature which you can do yourself, but I would suggest be careful when you are heating your mobile while doing that. Then beside that, we have a graph which shows a capacity of a cell, and if you see, the capacity of that cell is being affected because of the temperature. This is a discharge curve, and we can see the charge is 0.0 to 45 degrees and minus 30 to minus 20 to 60 degrees. And here if we see graph or the line with minus 20 degrees ends up much more before the typical capacity, which is at 25 degrees is the typical rated capacity, which is something around 3.25 Ah. And if we see, if we are discharging the cell at minus 20 degrees, it is ending before 2.5 Ah. And what is the reason behind that? The reason behind that is simply this, that the electrolyte inside the cell is frozen and it doesn't allow a complete reaction to happen, which means the ions are not completely transferred, and because of that there is only little bit of capacity that it could offer at that period of time. So that is what happens when you are trying to discharge the cell at sub-frozen temperatures. So in that way you can see a drastic capacity fall because of that. So what you could do that is, you could put a heater onto the cells, allow it to heat it up to certain time, and then you can start using the cell. Also, this is certain thing that when you overheat the cell temperature, you have a separator between anode and cathode, which we discussed in the first week. The separator is made of polymers or PP material or something, and it's of nano size. And when such amount of heat is being transferred, when the cell is being operated at such high temperatures, the separator between the cathode and anode melts. And when that melts, the whole anode and cathode are in contact with each other, which causes internal short circuit, and it can also lead to flames. So that's the reason BMS has to be very cautious, has to be programmed cautiously for higher temperature and lower temperature protection, so that the cells are steady and they don't enter into a thermal runaway state. Now let us understand SEI layer and its effect on capacity degradation. So all the above layers like overcharging, discharging, overheating of the cells, etc., can lead to an SEI layer formation, and this is something which increases the resistance of the cells and further deteriorates the whole cell and kills the cell at the end. So SEI layer is nothing but a solid electrolyte interface, which is formed because of all the abuses like overcharging, we have over discharging, we have abusive higher C rates, so we have high operating temperatures, and all these lead to a faster formation of solid electrolyte interface, and that is actually formed on the anode, which is the negative electrode. And let's get a little bit into the basics of cell. Like we have a cathode, and which is a positive electrode, which is a composition of LFP or NMC, and we have an anode which is basically of graphite and carbon. So during charging, what happens is all the lithium ions move from cathode to anode and they sit onto the anode. And when we are overcharging it, all these lithium ions go and fix to the anode so badly that they are plated onto the anode. And when overcharging happens many number of times, this lithium ions, if we see, they are fixed to this anode portion. And when we are discharging, all these lithium ions move back to the cathode from where they have come from. So by doing this, the lithium ions can come sit on the anode and they go back. And by overcharging it, some of the lithium ions still remain on the anode only. So when during the next process of charging, what happens is the next lithium ion which comes, it would not sit on the base, it would go and sit on top of the lithium ion. So what happens is by doing that, the lithium ion gets deposited one over the other and one over the other, like where instead of having a flat surface, we can see a lot of ions forming one top of the other, which could lead to dendrites. And when that dendrites are formed, the same happens when the dendrites are formed. It could puncture the separator sheet which is in between the cathode and the anode. That is where we get a short circuit, internal short circuit of the cell. And similarly, what happens when discharging? When we discharge the cell to a higher extent, then we are over discharging the cell. What happens is all the lithium ions which are going away are deposited on its cathode from where they have come from. And if we are over discharging the cell, the anode portion of it has a current collector which is made up of copper. And when we have such kind of copper ions, the copper ions also gets released, and because of which the metal contamination happens, and then again we have the same reason, which is the separator sheet tears off and there is an internal short circuit between anode and cathode. So the reason why this whole thing happens is because of we are overcharging the cell or we are over discharging the cell. And we also have abusive C rates. So abusive C rates are like the same when the cell is at lowest SOC like 5% and 10%, and even then we are trying to abuse the cell at 2C, 3C, when the BMS is not even bothered about that. That is where it happens, abusive C rate. And then what happens in the higher operating temperature? Nothing but the electrolyte gets dried up and there is no medium for the ions to transfer, and there could be salt remained on the separator sheet of the cathode, and that can cause internal short circuit as well. So there are n number of ways of SEI layer formation and the cell deterioration, and the main reason for that is the user's abusive usage, and if the BMS is not programmed properly, that is also one of the main reasons.